Hello, my name is Griffin Sipes. Thank you for your interest in my poster at ORS 2022. In this video, I'll give you a brief overview of my work. Fractures of the third metacarpal bone are one of the most common injuries in racehorses. These fractures occur early, between 2 and 3 years of age. The fracture patterns in the medial and lateral portions of the MC3 are different, and the lateral MC3 patterns are more common. The clinical problem we are looking at is the reason why horse fractures are different in the medial and lateral condyles of MC3 is unknown. Our hypothesis is that the structural and material differences in the medial and lateral condyle are different, and this implies that if bone properties are different, exercise interventions can be used to encourage bone adaptation in the MC3. Our study objectives were 1. Evaluate the structural and material properties in the medial and lateral condyles of the third metacarpal during growth, and 2. To assess the strain state over time in each condyle during trotting. We started with our calculation of structural and material properties. This was done using longitudinal computed tomography or CT scans. We had n equals 1 subject who had CT scans performed at 6 time points, 9, 17, 21, 25, 41, and finally 53 weeks. In the CT image here, we can see that our area of interest is the distalmost region of the MC3, and in the cross-section we broke up into 4 quadrants, the palmar, dorsal, medial, and lateral, and in this study we're looking at the medial and lateral quadrants only. A set of hydroxyapatite phantoms was included in each of these scans for us to calculate bone mineral density in each of the quadrants. And bone volume fraction was also calculated using custom MATLAB code. Next, we were able to use these material properties to assess the strain state over time by using subject-specific finite element models at 3 time points at 9, 25, and 53 weeks. These finite element models were created by segmenting the MC3 in a Mira, smoothing the model in GeoMagick, meshing it in Abacus, and finally assigning material properties inside of BoneMat. For each of the models, our boundary condition was to have the proximal half of the bone fixed, since we are only concerned about the distalmost portion of the bone. We assigned contact areas based on literature, of 1 small contact area on the lateral side and 1 larger one on the medial side. Compressive loads were also assigned based on literature. The MC3 has a maximum contact force during a trot of 38.4 newtons per kilogram, and 70% of the load is located on the medial side. And now moving on to our findings, we found that the lateral condyle of MC3 has lower cortical and trabecular bone volume fraction and lower bone mineral density. Looking at a plot of bone volume fraction against increasing mass during growth, we can see that trabecular bone volume fraction increased more rapidly in the lateral region compared to the medial region, and medial cortical bone volume fraction was almost 2 times the amount of the lateral. Also, medial cortical bone volume fraction increased faster than the lateral side. Similarly, looking at bone mineral density in units of milligrams hydroxyapatite per centimeter cubed, again against increasing mass during growth, we find that cortical bone mineral density was 7.5% higher on the medial side compared to the lateral, and cortical bone mineralization rate was much higher on the medial side compared to the lateral. And finally, medial and lateral bone mineral density of trabecular bone increased at similar rates. From the finite element models, we found that local peak compressive and tensile strains are distributed heterogeneously in the distal MC3 bone during trot. We found that maximum principal strains during trot were greatest in the medial quadrant compared to the lateral, and compressive strains were highest in magnitude in the medial quadrant and towards the growth plate. And finally, tensile strains occurred primarily in the lateral region, and they also increased with growth. From these results, we conclude that there are significant structural and mineral density differences between the medial and lateral condyles, the MC3. Higher principal strains in the medial quadrant may contribute to increased growth and mineralization rate of cortical bone in the medial condyle. And finally, the area of high tensile strain in the lateral condyle may predispose the bone to fracture. However, the study is highly limited by its number of subjects, as we only had one, and further study is needed to validate our results. We would like to thank Grace and Jockey Club Incorporated for funding this project, and thank you for expressing interest in our project. If you have any questions, feel free to find me at the conference or send me an email.